Hi everyone. Uh, so this is where we were in the last class. We were talking about ISR implementation. We had seen that the main things in the ISR is the first thing is if multiple devices can generate the same interrupt or can cause the same handler to be triggered, you have to figure out which device actually caused the interrupt, right? And then we have to identify the exact condition within the peripheral which generated the interrupt, because each peripheral could generate interrupts for multiple reasons, and then do the bare minimum required to deal with the cause. So don't do much of data processing in your code. Only do the minimum that is required to deal with it. Like for example, if a new data is available, grab it and store it somewhere and put up a flag for your main program to access it, right? Do not do much processing. And as a general rule, the higher the priority of interrupt, you put in more effort to make it shorter and shorter. And please note that when I talk about a shorter code or shorter ISR, I am not talking about the number of lines in your code. I am talking about the time taken for it to execute. And to be more precise, or to be precise, the worst case execution time. Okay, we sometimes say WCET, because your execution time for the same service routine might not be the same all the time. Why? Because it might contain conditions like if else, right? Sometimes you might be doing the if part, sometimes you might be doing the else part, which might have different execution times. So if something, else something, so if condition something, so this if might have further ifs, etc., etc. So depending on the exact scenario, depending on the exact conditions, the time taken could vary. But if you look at your program carefully, you can always analyze what is the worst case scenario, right? And that worst case execution time should be as short as possible for higher priority or more important interrupts, because you should still complete the interrupt before the next interrupt from the same peripheral comes in, right? Like for example, for SysTick, you have to handle everything in 1 millisecond. Otherwise, you will have loss of data, or you will lose your sense of time. And do not block your ISR. That is, do not have any blocking code. A blocking code is something which waits for something to happen. For example, your temperature sensor waits until you get 340 cycles or something, right? So it is waiting for some condition or something to happen or something to be completed. Never, never, never wait inside the service routine. Okay? So you should not have a situation where, for example, you wait for a particular input to be asserted or for a particular value to reach a certain level. No, not inside your service routine. Your service routine should be lean and mean, as lean as possible. And any variable modified inside the service routine should be declared as a volatile, so that the compiler knows that it is not supposed to optimize away the variable or make any assumption regarding the value of the variable. Okay, so whenever you have a variable being read it really from the memory location. And when you are writing a variable, write to the real memory location rather than making assumptions about it. Then the last step is clear the interrupt. Clearing the interrupt is essentially telling the interrupting device that, okay, I listened to you, or I have heard you. Could you please deassert the interrupt? Okay, and that is done in different ways. Uh, and the exact way in which you do it depends on the peripheral, and the exact channel that you use for clearing the interrupt is the channel through which you talk to the device, or the interface through which you talk to the device. For example, if an I2C device generates an interrupt, like for example, uh, an I2C slave like light sensor generates an interrupt, you have to tell the light sensor to deassert the interrupt, right? So how do you tell the light sensor? Through the I2C interface. That's the only interface you have, right? So that's how you do it. Nothing standard about it, and clearing interrupt has no involvement from the NVIC. Okay, so it is not something which is done at the NVIC side. And then exit the handler, and this is where I was at before we left for, or before we finished the last class. Clearing pending status is not the same as disabling an interrupt, which is not the same as clearing an interrupt. Disabling pending status is something which is done at the NVIC side, right? So not disabling pending, clearing pending status. So you clear the pending status to prevent the interrupt from being executed, right? Clearing pending status. If it is currently pending, just remove the pending status so that interrupt will not be executed. Then disabling an interrupt is preventing the interrupt from becoming active. So if an interrupt is disabled, it can go pending, it cannot go active. So the pending to active transition is blocked if the interrupt is disabled. Disabling an interrupt is also called masking an interrupt. Okay, because the interrupt is effectively covered with a mask. You can't really see it. Then clearing an interrupt is a totally different thing. It is something to do with the interrupting device. Okay, it has nothing to do with the NVIC. Whereas the first two are NVIC related stuff. You do that by writing or reading, in this case, writing certain registers within the NVIC. The first one is done by writing to interrupt clear pending register. This is done by writing to interrupt clear enable register, and this is very much peripheral dependent. There is nothing standard about it. Clear? Now just a final example before we wrap up this chapter. Suppose if I want the priority group setting to be 5 for whatever reason. When priority group setting is 5, 2 bits are used for preempt priority, 3 are used for sub priority, right? Then let's say my preempt priority is 1 1. Sub priority is all zeros. Let's say that is what I want to do. Preempt priority of 1 1 is going to be high or low? I mean, is it a high priority or a low priority? It's a low priority because 1 1 is the worst case, right? If you have 2 bits and if both of them are 1, it means your preempt priority is the lowest in the system. Now the full IPR content would be the first 2 bits will be preempt priority, the next 3 bits will be sub priority, and these 3 bits are actually not used, so you will be writing zeros there. So the actual content that you write to IPR is C0. Again, it's a bit tricky. I mean, it's a bit confusing what exactly IPR is. It could be, sometimes it is used to refer to a 32-bit register, sometimes it could be used to refer to an 8-bit register. Anyway, here we are talking about the 8-bit register, or to be precise, it is actually the pri field in an IPR. The priority level field in IPR. There are 4 priority level fields in each 32-bit IPR. So you will do set priority grouping 5 to set the priority grouping to 5. Then set priority EINT3 underscore IRQN, which is the IRQ number for EINT3, which is what we use for GPIO, because GPIO and EINT3 share the same interrupt position in the NVIC. In fact, they are considered the same interrupt by NVIC. In other words, NVIC only recognizes EINT3 IRQ. It doesn't recognize GPIO directly. GPIO is piggybacking on EINT3. Then the value that you pass to set priority function is hex 18, but the actual value that you write to IPR is hex C0. Why this difference? The set priority function, if you remember, I mentioned in the last class that set priority function is designed to rotate the value that is given to it by 8 minus number of priority bits. The number of priority bits in LPC 1769 is 5. So it will be, this will be rotated by 8 minus 5, which is 3. What is hex 18 rotated by 3? I'm not going to show it, or rather insult you by showing it at this stage of the module. It is C0. You can easily figure out, right? Just add 3 zeros. In other words, if you look at this alone, this is nothing but hexadecimal 18, right? 18. So for set priority function, you will give a value which is to be returned to the available number of bits. So IPR has up to 8 bits. The available number of bits in this case is only 5. So you write hex 18 to this location, which is effectively writing hex C0 to the whole 8-bit location. Okay, so that's the idea. And then it's always a good idea to clear the pending status before you enable the interrupt, so that any interrupt which had occurred in the past which caused the pending status to be high will not cause the interrupt service routine to be triggered immediately once you enable it, right? Now, this is a bit of a crude way to do things. A slightly nicer way to use the set priority function is to call the encode priority function before you call the set priority function. Because remember, encode priority function is a function to format the priority in such a way that it can be used for set priority function. So you see, you will call the encode priority function with the arguments priority group, preempt priority, sub priority. Priority group is 5, preempt priority is 1 1, sub priority is 0 0 0. So you call the encode priority function, which will combine it into this answer, which is going to be hex 18. And then you will just call the set priority function with the second argument as whatever you got from the encode priority function. So this makes your code much more readable and less likely to make mistakes as compared to using or hard coding hexadecimal values. Okay, so that's it. So the eventual value that is returned to the IPR by this function is hex C0, even though you are passing 18 to the function, because 18 will be shifted left by 3 positions before being returned. And then you have to create the exception handler. And I already gave you the guidelines for exception handler creation. So use that, and eventually when you are done with it, you return from the function. So the interrupt handler name should match interrupt handler name in the vector table to ensure that the vector is set up in the vector table correctly. So in this case, you have to use the exact name EE2024 underscore IRQ handler. You cannot use any name you like. And do you know where these names can be found? In fact, it's fairly easy to write. It's just the whatever interrupt name underscore IRQ handler. But you can find the name in core CM3 file. There is a core underscore, sorry, not core CM3. There is a CR startup file, some CR underscore startup file, which will be there in your project. Okay, startup. So you can see all the interrupt handler names in that file. There is a CR startup.c file. You can see the names there. Even otherwise, like I told you, it's fairly straightforward to figure out. But it has to be exact. Otherwise, your vector table will not be set up properly, which means your interrupt will not really work properly. Okay, if you use any other name, it will be considered just like a normal function, because C language does not discriminate between a normal function and an interrupt service routine. The C compiler doesn't know. Okay, so there is a certain set of names defined to initiate the vector table appropriately, and that is done in the CR startup file. And you have to use the exact name for it to be set up correctly. Then how do you trigger the interrupt finally? One is you can wait for the real condition to happen for the interrupt to be triggered, which could be an external interrupt, including GPIO interrupts to EIND3, which is the case in this example. Then another option is setting a pending register in NVIC. What would be the use of the second one? You are manually or artificially triggering the interrupt, which could be useful for testing purposes. Like I told you earlier, you can't really go and crash a car to see whether the airbag system works, right? You should have some mechanism to test or simulate the scenario. And you can do that by just writing to set pending register, interrupt set pending register. And the third option is there is a register called STIR, software trigger interrupt register. And writing to software trigger interrupt register can actually cause any interrupt to be triggered. So you write the exception number to STIR, exception number or IRQ number, one of the two, I can't remember exactly. So that will cause the interrupt to be triggered. Okay, so both are somewhat similar but slightly different, and in many cases it might be just easier to just use STIR followed by the exception number. Okay, and then the corresponding exception will be triggered, exception or interrupt. Got it? So that is it for interrupts. In fact, there are some interesting interrupts which you want to read up about, like for example SVC. SVC is an exception. It's called supervisor call. Do you know what is this for? You know, when something prints hello world to the screen, you know, you write a printf hello world in your, let's say, a normal C program, not running on LPC 1769 on a conventional computer. How does it work? Is your program writing directly to the screen? No, your compiled version of the program does not have any information regarding how to write to the screen. All it does is it will format the data properly and place it in some location and then tell the operating system, could you please send it to the screen? Then the operating system comes in, invokes the appropriate drivers and puts the required data onto the screen. Okay, so that is how it works in a real computer. So whenever there is an operating system, you never really interact directly with the hardware. Whenever you want to read a hardware, you request the operating system to read it for you. And then the operating system will come in, invoke the appropriate drivers and then read it. Okay, that's what happens in a normal computer. And that's why these days, it's not so easy to crash your operating system by writing bad programs, which was quite easy in the days of like Windows 95 and Windows 98, which I used to use when I was in college. So it was quite easy to crash systems because direct hardware access was permitted. But modern operating systems do not allow user programs to access hardware. So whenever you want to access hardware or get some service from the operating system, you call the operating system by invoking SVC, which is an exception. Okay, then the operating system comes in, looks at what you want to do and will do it for you and then give back control to your program. Okay, so the operating system is also the one which allows multiple programs to run at the same time. Like for example, sometimes you might be typing a report in Word while you are downloading something legal or illegal using BitTorrent or whatever, and then you might be, for example, running some simulation or compilation in the background, etc., etc. So you can see, you will get the illusion that multiple programs are running at the same time, even though you might have only a 2-core or a 4-core processor, right? So how does it happen all together? Because there is an operating system. So what the operating system does is it will give one slice of time for a particular program. For example, it will decide or it will divide 1 second into 1,000 different parts. Okay, and it will give one part to MS Word, allow it to run. Okay, and then once 1 millisecond later, your sysdig will trigger an interrupt, and the interrupt service routine is a part of the operating system. So the operating system gets control after every 1 millisecond. So after 1 millisecond, it will cause your MS Word to be suspended and it will run another program. Will allow it for another 1 millisecond. Then it will suspend it again. Allow the third one to run. So it will do it in a sort of a cyclical way. So the user gets an illusion that all these programs are running at the same time. Though in fact, if you have a single core processor, you have only exactly one program running at any instant. Got it? So this process of switching between programs very fast is what we call multitasking. And multitasking is accomplished mainly by the use of a SysTick timer. And that is the main use of SysTick. It's for the operating system to manage multiple programs. Okay, to ensure that it gets controlled periodically so that it can suspend a program and start the next one. Got the idea? Now, can you do this in LPC 1769? The answer is an emphatic yes. There is a free operating system available for LPC 1769 called FreeRTOS, free real-time operating system. So if you want multiple things to happen in parallel, you can write each of them as a more or less separate program or function. So you can essentially have multiple equivalents of main function in your program. And all these so-called main function equivalents will appear to the user that they are all running together. Okay, so if you have to do multiple things or deal with multiple sensors, etc. in parallel, you can actually do that quite easily using a real-time operating system like FreeRTOS. And that will make your project 2 or assignment 2 quite a lot simpler if you know how to use it. If it's not particularly hard, but your live MCU doesn't work with the FreeRTOS. FreeRTOS works with a newer version of live MCU called LPC Open, okay, which is a even higher level interface as compared to your live MCU, which has good and bad aspects associated with it. When it's very high level, it's generally easier to use for somebody who doesn't know the hardware. But for you, you are trying to understand the hardware and how the software interacts with the hardware, right? So for you, from a learning perspective, using LPC Open is not a very good idea. But if you want to use it, go ahead, no one is stopping you. Okay? I was just mentioning it as an additional thing because in real life, if you have a complicated system, you almost always use a real-time operating system, which makes your life a lot easier. Okay? And each main program equivalent that runs in the system is what we call a task, or sometimes they call it a thread. Okay? If you are interested, you can read up more about it, or there are some modules where you can learn more, like for example, CS 2103 operating systems, or CG 2271, which I am not sure if you can take, real-time operating systems for CEG students. And there is this module I teach, EE4214, which may or may not be offered by the time you get to that level. But that is where this kind of things can be understood in more greater detail about how operating systems really work and how you can make use of operating system to make your life easier. Okay, so that's about it for that chapter. We are going into the last major chapter, which is UART. Oops, give me a moment. Okay. Sorry, I have loaded the wrong file, but never mind. This is good enough. So we will start with UART. UART is Universal Asynchronous Receiver Transmitter, which is a standard for long distance asynchronous serial full duplex peer-to-peer communication. Now let us look at each of the words. You already know it's long distance, which means it's not really used for short distances, usually not. The distances that you are looking at could be from few centimeters to thousands of kilometers. Okay, so UART can be used for really long distance communication. Asynchronous, anything long distance is almost always asynchronous. Why? What is the problem with synchronous communication over long distances? Your correspondence between data and clock could be lost, and your clock might be more harmful than useful if you transmit it over long distance, right? Serial, you are sending bits one by one, so only one wire is used to carry one byte or one word of data. So you will be sending bits one by one. Then full duplex, you will be sending and receiving at the same time, which means you need to have at least two wires. Okay, half duplex variants exist, but in the basic form, UART is meant to be duplex. Peer-to-peer communication, it is between two equals. There is no master or slave in the system. Okay, both the parties have the ability to initiate communication at any time they want. So there is no master slave system. And it is a communication between just two devices, which means there is no real addressing. There are only two devices which are talking to each other, so there is no problem related to addresses. You don't really have to specify whom you are talking to because one set of wires is used for only one device. UART transmitter takes bytes of data and transmits the individual bits in a sequential fashion using a parallel in serial out shift register. Okay, so the UART fundamentally is just like any other serial communication mechanism. The transmitter side gets the data in parallel from your processor. So this is usually your processor, right? So the processor writes in parallel to the transmitter. The transmitter takes it in parallel form and shifts it out bit by bit through a serial interface. So the main part of your transmitter is a parallel in serial out shift register. And this line is what we usually call TX, or some people also use TXD, transmit, one single wire. At the destination, the receiver UART reassembles the bits into complete bytes using a serial in parallel out shift register. Okay, so you send it to some device and the receiving device will take it in serial form and convert it to parallel, which will eventually be read by the processor. Okay, so the two processors at the two ends talk to each other with the help of the UART interface. So this is nothing but a serial in parallel out shift register, which takes in serial data and gives parallel data to the processor. And this is usually what we call RxD or Rx, receive. Okay, and in most cases, there is another wire going in the opposite direction. Now, just like how most roads have two lanes, right? One lane for one direction, another lane for the other direction. So one lane is called TXD, the other one is called RxD. So from the perspective of a particular device, TXD is an output, RxD is an input. But the output from one device will become the input to the other device. So Rx is an input for this device and TX is an output from this device which will become Rx for the other device. So the TX and Rx are connected in a crossed manner. UART refers to the logical layer and usually does not perform end-to-end communication between computers directly. Now this is very, very important, and this is a significant difference from your I2C. In I2C, you send data directly onto the set of wires you have, right? Whatever you send is received directly, there is no intermediary. So if two devices are talking to each other using I2C, they connect to the same set of wires, and whatever you send here will be received directly. Whereas UART is usually not meant for direct communication between devices. So the two UARTs on the two sides do not generally talk to each other directly, because UART only specifies the logical layer of things, logical layer of communication. What do you mean by logical layer? We are talking about ones and zeros, but we don't bother about how ones and zeros are transmitted. In real life, ones and zeros are transmitted in a slightly different way. Okay, which is through some physical layer. We will see this here. So the communication is usually done in conjunction with some standards such as RS-232, ZigBee, Bluetooth, etc., which includes some sort of physical layer. So logically, the two devices might be communicating using UART, but the real physical communication could happen through some other means, some physical layer. And the physical layer protocols could be RS-232 or ZigBee, and you are using a version of ZigBee called XB. You have your XB modules, right? Which is nothing but a wireless UART. So there is a separate physical interface for UART transaction. So when you convert your cable-based UART communication into XB communication, you need not change your program at all. Okay, so the program still sees it as UART, but the exact physical mechanism for communication changes. Right? When you are using a cable, what is the exact physical mechanism used for communication? It's electrical signals, but which exact protocol you are using? The underlying protocol is USB. You are using USB to connect the two devices together, right? You are connecting it using a USB cable. So in fact, the scenario is kind of like this. You have your UART here. You have your UART here, but in between, so this is UART and this is UART. So your LPC program sees it as a UART. Your computer, which is your Teraterm, also sees it as a UART. But the underlying communication actually happens using USB. So the logical layer is what connects this and this. The physical connection is actually a USB connection. And later on, you will change it to an XB connection. It could be Bluetooth, or it could be some other similar standard. And this standard is usually a part of your physical layer. Physical layer is the actual physical mechanism used for communication, which could be a number of different ones for UART. The external signals may be of different forms. It could be electrical signals like RS-232, RS-422, RS-485, and even USB. Some do not use electrical wires like optical fiber, IRDA, Bluetooth, etc. Okay, IRDA uses infrared, Bluetooth uses wireless at 2.4 gigahertz, and optical fiber uses optical pulses, right? And this is a main mode for internet access for you, right? Like for example, if you are a local, if you have a home here, you will almost certainly have an internet connection, and it almost certainly is a fiber connection, right? You will have a few hundred Mbps connection, so you'll have a fiber modem. So that modem actually translates electrical signals into optical signals and then transmit it. Could also be IRDA, which is supported by some of the phones. Some phones have an IR blaster, right? Okay, IRDA is not exactly the same. It's mostly out of fashion now. Then you have Bluetooth. Yeah. And transmitting low voltage digital signals over long distances is not practical. Why? What will happen to the digital signals if you transmit over long distances? Sorry? Yeah, it will undergo some kind of distortion or attenuation, right? Do you know the exact reason for that? Of course, the resistance of the wire matters, so that will cause some kind of signal losses. Other than that, sorry, sorry. Yeah, there could be interference between other signals, and the number one reason for not transmitting digital signals over long distances is, how many of you have studied EE2023? How many of you know what Fourier transform is? Most of you know, right? What is a Fourier transform of a digital signal or a continuous pulse signal like this? It's like a sync waveform, right? Something which looks like this. Sine pi t by pi t kind of thing, or pi omega by pi omega kind of thing. So you can see that if you see the Fourier transform of a digital signal, it is endless. It's not finite, which means a digital signal contains all frequencies up to infinity. And most of these so-called sharp transitions are because of higher frequencies. But most practical systems act as low-pass filters. It does not allow high frequencies to pass through that easily, most practical systems. Okay, so even if you send something like this, at the other end, most of the higher frequency stuff are cut off. Only lower frequencies remain. So what you will end up with is something which is very similar to a sine wave, which has a frequency which is the same as the fundamental frequency of the digital signal that you are transmitting. But at the end, when you receive it, it doesn't look like a digital signal anymore, right? You might not be able to discriminate clearly whether this is a 1 or a 0, which is not very good. And that's why you do not transmit signals over long distances in purely digital form. So many physical layer standards use modulation, some kind of modulation, which is also called keying when the modulating signal is digital, modulation of a carrier signal. Okay, so some modulation of a carrier signal is used. Like, I have it in the notes that is given to you. Sometimes you modulate the frequency of a sine wave, sometimes you modulate the amplitude, sometimes you modulate the phase, etc. Like for example, if I want to send 101, if I send it using frequency modulation, it will look kind of like this. So this part is to denote 1, this is to denote 0, this is to denote 1. Different frequencies for different inputs like 1 or 0. Sometimes it could be amplitude modulation, in which the frequency doesn't change, the amplitude could be like this. Okay, like this for 101. So higher amplitude for 1, lower amplitude for 0. But the eventual signal that you transmit is not digital, it is analog. So you are taking an analog signal, a sine wave, and changing some property of the sine wave. And that process is called modulation. And if the modulating signal is a digital signal, it is called keying. Okay, but the term modulation is also still used. Like, in cars, etc., you might listen to FM radio, right? FM is frequency modulation. So you are modulating the frequency of an analog signal based on another analog signal, because a FM signal is still eventually analog. The modulating signal is analog. Modulating signal is a signal which is causing the property change of the sine wave. And the sine wave itself is called carrier or modulated input. Okay, so when I talked about 101, this is essentially the modulating signal, and this is the eventual signal. Okay, after modulation, and you modulate the property of a constant frequency, constant amplitude input called a carrier, and this is a modulated output. Now on the receiving side, you take this analog signal, the modulated signal that you receive, and then recover the original modulating signal from it. The modulating signal is what contains the information, right? So you recover that information from the modulated signal, and that process is called demodulation. Now, does it sound very similar to a device which you use for your home internet connection? Heard of modems before? What is modem? Modulator, demodulator. Okay, just a abbreviated version of modulator, demodulator is modem. So whatever you send is modulated, and whatever you receive is demodulated by the modem. It could be modulation of audio signals with with phone line modems. Have you used a telephone modem, dial-up internet connection? Maybe not, but when I was like 15, 16 years old, when internet came along, most of the connections were dial-up connections. Okay, unless you are a millionaire, you probably wouldn't be able to afford a broadband connection. And even broadband connections were few hundreds of kbps broadband. Okay, and normal connections were like 56 kbps. So you connect your telephone modem uh, to your computer. Sorry, you connect your telephone wire to your telephone modem and connect the modem to the computer to access internet. And then you dial to the internet service provider, and the information was transmitted as modulation of audio signal. So if you pick up your telephone while you are doing this communication, internet communication over the telephone modem, you can see all these kind of funny sounds like audio clicks, because those clicks were used to send ones and zeros. And then modulation of radio frequency signals are possible. Like for example, if you have a 4G or 3G dongle using which you can access internet, right? So your information is used to modulate a radio frequency signal, which is usually at a frequency of something like 900 megahertz, or in Singapore they mostly use 2100 megahertz. Okay, so that is a modulating, or sorry, that is a carrier signal that you use. It's an RF signal, radio frequency signal. Or it could be modulation of power line, which is also used for communication with very remote parts. So the old dial-up scenario, which I was talking about, was kind of like this. So you had your UART in your computer, which connects to the modem using a physical layer standard called RS-232, which we will see very briefly towards the end of the chapter, which is mostly obsolete. And then you have a modem here, and this modem connects to the modem on the other side. And the modem on the other side is essentially your internet service provider's modem. And that itself is connected to the UART of your internet gateway, the so-called internet gateway of your service provider using a UART. So your UART establishes a connection with the UART of your service provider, okay, so that you can access internet. These days, the modem is usually a cable modem or optical fiber or an RF modem. So if you still have your StarHub cable-based connection, you will have a cable modem which still uses electrical signals, which are used to modulate, or which uses the digital signals to modulate an electrical signal, or optical fiber, which has digital signals transmitted as light pulses, okay, and so on. Many users use software, sorry, many user software use UART for communication due to its simplicity. Like for example, if you have a internet dongle from Singtel or StarHub, have you seen those? Like those USB dongles, you can just plug in, put in a SIM card, and you can access internet. Haven't you seen it? I think you can buy it on StarHub and Singtel websites, etc. I'm sure there are a lot of people selling it on Carousel. So if you are curious enough, just buy it, put in your SIM card, and you can access internet anywhere, anytime, as long as you have a data connection. So even that dongle uses a UART on its software interface. So once you plug in the UART, assuming that the drivers are, sorry, once you plug in the dongle to your computer, assuming that the drivers are installed, you can see a new COM port appearing. Have you seen COM ports in Windows? Okay, when you plug in something, like I can show you. So you can see these, right? Like COM31, COM32, etc. Those are actually COM interfaces created by Bluetooth devices. So even though my communication might actually be happening through Bluetooth, the underlying software can simply see it as a UART. So your programming is really easy. Sending something through Bluetooth is as simple as sending something through this interface. Okay, and the software interface for UART is a lot less complicated than, for example, Bluetooth. So even complicated protocols like Bluetooth sometimes have a higher level UART which is used to interface with the software. So writing a program to write to this COM port is very easy. You can even write to this COM port using Teraterm. Okay, and that will be sent over your Bluetooth interface. So that's the idea. For simplicity, you might use UART as an underlying protocol. It is translated to actual physical protocols such as USB and Bluetooth by either hardware or software mechanisms. So, for example, you have a USB UART bridge called FT232R or similar ones on the baseboard. So, if you look at the baseboard, your LPC 1769 has a UART within it. So, you have TX and RX signals going out, but it doesn't go out as such all the way until your computer. It goes into a chip called USB UART bridge. And the most popular one is FT232R. And there are some others available, but this is probably by far the most popular one, 232R. So this will take in all these UART signals and convert it to USB signals. So the user programs do not really need to deal with a complicated protocol like USB. USB is very, very complicated. You don't have to do or understand USB protocol. You can just use UART and it will be translated to USB, which will be sent to the computer. On the computer side, you have a virtual COM port driver, which will convert the USB data into UART. So the Teraterm software will see it as a physical UART available on the computer. But the actual conversion is managed by a driver. There is a driver program which is provided by the manufacturer of this device, which will convert it to UART. Okay, so this is a communication scenario for your assignment 2. And if you are using your XB, then instead of this, you will have the XB module here and the XB module here connected to the computer. Okay, and the XB module will be plugged in through the USB, and the driver will again do the conversion to UART. So the software doesn't really need to know whether it is a hardware UART or a soft UART. It will just see it as UART and it can talk to that particular UART. Okay, so that makes your life a lot easier. And you can see in the following slides that UART is a really simple protocol, even much simpler than I2C. So it's quite easy to communicate using UART. Now let us look at the character framing of UART. How data is sent using UART protocol. Each character is sent as a logic low start bit. A logic low start bit signals the receiver that a new character is coming. Okay, so all communication starts with a start bit. And the start bit here is a logic 0, logic low. It signals the receiver that, okay, a new character starts. Now, based on this, can you tell me what is the default condition of the line? Like for example, this is your transmitter and this is your receiver. And for now, just think of it as a direct connection. So this is what we call the RX. This is this is a TX and this is a RX. Okay, transmit, which is an output of the transmitter, receive, which is an input to the receiver. Now, what will be the default condition of the line? So if you hook up an oscilloscope onto the line, when no communication is taking place, what will be the condition? Yeah, it should be high, right? So that you can uniquely distinguish and figure out that, okay, a new data is coming in when it goes low. So the default condition is high. And when it goes low, it signals the beginning of a new character. And in UART, data is sent as characters. And one character can mean 5 to 8 bits. It can be 5 bits, 6 bits, 7 bits, 8 bits. But usually it is 8. 99% of the real world systems use a character size of 8 bits. But there could be systems where the number of bits within a character is not 8. And LSB is sent first, unlike I2C. Okay, so the first data byte sent is LSB, the last data byte sent is MSB. In I2C, it's the other way around, right? MSB is sent first. And you have an optional parity bit for detecting bit errors. What is parity? Heard of parity before? What is it? I'm not talking about the parity when it comes to economics or those kind of stuff. Parity simply means equality in some sense, right? But what is parity with respect to our module, or parity from the perspective of an electrical or computer engineer? Parity is a simple mechanism to detect bit errors. Okay, I'll give you one simple example. Let's say I am transmitting this character 1010. I am receiving it at the receiver end. I need to know whether the data has any error or not. Can you think of any mechanism to do that? One simple mechanism is, instead of transmitting 4 bits, transmit 5 bits. The fifth bit will be an XOR of all the bits. What will be the XOR of 1, 0, 1, 0? XOR all the bits. What will it be? 1 XOR 0 XOR 1 XOR 0. Yeah? Yeah, it will be 0. Why? Because in XOR, two ones will cancel each other. 1 XOR 1 is 0, 0 XOR 0 is 0. So to find the XOR of a large number of bits, just count the number of ones. If the number of ones is odd, then the XOR of all the bits is 1, otherwise it's 0. Like for example, 1 XOR 0 XOR 1 XOR 1 XOR 0 XOR 1 XOR 0 is simply 0. You count the number of ones. It is even, so it's 0. It's odd, it's ones. And what is the advantage of sending these 5 bits? Let us say on the receiver side, what you receive is 11100. You compute the XOR of all these bits and check against this. Are they the same? No. Then you know that there is definitely a 1 bit error. But then you might ask, what if there are 2 bits which are going wrong? They sort of cancel each other, right? Well, there is no way to detect it using such a simple parity scheme. This sort of a scheme is what we call a parity scheme. Adding that extra bit, which is an XOR of all the bits. You can detect only up to 1 bit error. If 1 bit has gone wrong, on the receiving side you will know. Irrespective of which bit has gone wrong, you will definitely know. If 2 bits went wrong, you wouldn't know. But many a times you can make statistical predictions, like the probability of 1 bit going wrong is, let's say, 10 raised to 1 by 10 raised to 6 or 10 raised to minus 6. The probability of 2 bits going wrong would be 1 by 10 raised to 12, which is 10 raised to minus 12, which will be very low, right? So many a times you can just assume that only 1 bit will go wrong. And then this sort of a scheme can already know whether the bit that you are getting is not bit, the character you are getting is correct or not. So this sort of schemes are what we call parity schemes for error detection. Okay, this is a simple scheme used in UART. There are more complicated schemes available, uh, which is a very interesting field of mathematics in itself, coding theory. You can actually read up about it if you are interested. Okay, another simple parity based scheme is Hamming codes. You can read up about it if you are interested. And more complicated schemes are used in your communication with the cell tower for your phone. Your phone talks to the cell tower, right? And that also uses these kind of parity schemes. But it's not a simple parity scheme, it's quite complicated. And that is a basis of what we call CDMA. Heard of it before? CDMA? Yeah, code division multiple access. It's not particularly hard to understand. If you are interested, please do read up, or you can come to me later. I can explain it to you, but not in the syllabus, so I'm not explaining it now. But this is a fundamental technique that is used for your phone to talk to the cell tower. Okay, it's a very beautiful technique, which was invented by a beautiful Hollywood actress. Heard of it before? You can Google about this actress called Hedy Lamarr. Okay, she was a Hollywood actress, and she is the one who invented uh, CDMA. Not really CDMA, the precursor of CDMA. Now, that is a use of parity bit. Then you have one or more stop bits, and stop bits are logic high. It is to signal the receiver that the character has completed. So once a character has completed, you will have one or more stop bits. That is configurable. You can define how many stop bits you want. Most systems use only one stop bit, but there could be systems with more number of stop bits. Right? So the stop bit is a logic 1. Now, the line will remain high until the next start bit. So since the start bit is a logic low and stop bit is a logic high, there is always a clear demarcation between the previous character and the next one. So in some sense, stop bit defines the minimum period of time for which the line is guaranteed to be high before it can go low again. When will it go low again? For the next start bit, right? So before the next start bit can come in, you need to have a stop bit which is at least one logic high. It could be more than one, which means it is guaranteed that the line will remain high at least for that many number of bits before it can go low. And that allows you to have a clear distinction between the end of one character and the beginning of the next one. Okay, and this whole thing, that is a start bit, a set of data bits, optional parity bit, and one or more stop bits all together is what we call a frame. Okay, so a character is sent as a complete frame by attaching certain bits to it. So you attach a start bit which is a logic low, you might have an optional parity bit, and you have a stop bit, at least one stop bit which is a logic high. This whole thing together is what we call one frame. Got it? So all the operations of a UART hardware are controlled by a clock signal which runs at a multiple of the data rate. So each data bit is as long as 16 clock pulses. Give me a sec. Yeah, here. So all operations are controlled by a clock signal. So the clock signal runs at a speed which is much higher than the rate at which your data comes. And usually it is at least 16 times. Okay. So each data bit is as long as 16 clock pulses. So one data bit has a duration which is equal to at least 16 clock pulses. The number is fixed, and for now, for this example, I'm just going to use 16. So the receiver tests the state of the incoming signal on each clock pulse, looking for the beginning of the start bit. So the receiver will keep looking at the incoming data very fast, 16 times a second, 16 times during the bit period. This is what we call one bit period. Okay, the time for one data bit, and it looks for that to look for the beginning of the start bit. So it's clarified here. So this is a time when the line is high, right? So when the line is high, when the condition is default, the receiver will keep sampling the incoming line very fast. Usually 16 times per bit period. And then if your 8 samples that you get are all zeros, then that point is considered the middle of the start bit. So if your sample data remains low for at least 8 samples, then it's considered the middle of the start bit. Why? Because a start bit has a duration which is equal to the bit period, and you are sampling 16 times per bit period. So if 8 of the samples are 0, the time at which you get the 8th 0 sample is considered the middle of the start bit. So you oversample the incoming line to find the middle of the start bit. Once you find the middle of the start bit, what will you do? You wait for 1 bit period. The bit period is agreed upon by the transmitter and the receiver. Okay, so both the parties agree on how long each bit is going to be. So you already know what is a bit period. The only thing you don't know is when does the bit exactly start. You know the duration for 1 bit, but you don't know where exactly it starts. So what you do is you wait for 1 bit period from the middle of the start bit, then sample the first bit. So you are sampling at the middle, hopefully at the middle of the bit. And sampling at the middle of the bit gives you the best chance to get the data or read the data correctly, right? If you go towards either edge, you are running a risk because the edge could vary slightly. But the middle is where you are most likely correct. Okay, so you take this bit, and this bit is clocked into a serial in parallel out register. So this is your sampling circuitry which will perform the sampling, and the bits are logged into a serial in parallel out shift register. Then you sample the next bit, then you shift it into the register and do it for 8 clock periods. And once you do it for 8 clock periods, all your 8 data bits are available here. Got the idea? So this is a fundamental principle of UART. And you also sample the 9th bit and possibly the 10th bit, depending on the number of stop bits, to make sure that they are ones. If the stop bits are found to be not ones, it means your sampling was definitely wrong. Got the idea? Because stop bit is supposed to be 1. If you are sampling at the correct times, it's supposed to be 1. So if the apparent start bit lasts at least 1/2 of the bit time, which is for 8 samples, right? Then it is valid and signals the start of a new character. If not, the spurious pulse is ignored. So for example, if you find that some of these samples were zeros, some were not, you will just ignore it. You will consider it as just noise or random stuff. After waiting for 1 bit period, 1 further bit period, the state of the line is again sampled and the resultant level is clocked into a shift register, which is what I just mentioned. You wait for 1 bit period time after the middle of the start bit and clock the sampled data into a shift register. Sorry. After the required number of bit periods for the character length have elapsed, for example, if you are expecting a character which is 8-bit long, you will sample it 8 times, and once it is done, the content of the shift register is made available to the receiving system. So here you see the shift register is essentially read by your processor. Okay, so your processor should read it only after all the 8 bits have been received. So there is usually some kind of a mechanism to tell the processor that a new data is available, some kind of a flag. So the UART will set a flag indicating a new data is available and may also generate a processor interrupt to request a host processor to transfer or to receive the received data, to read the received data. Okay, so it could just create a flag, or it could create an interrupt which will be used by the host processor to as an indication that a new data is available, so I should go and read it. In some common types of UART, a small first in, first out buffer memory is inserted between the receive shift register and the host system interface. This allows the host processor more time to read the data and prevent loss of received data at high rates. So usually the processor doesn't read from the shift register directly. Instead, the received data will go into a temporary storage location, which is what we call FIFO, first in, first out memory. Okay, and the typical size of your FIFO is 16 characters. So before the processor should start reading, you can receive up to 16 characters. If the processor doesn't start reading before the 17th character comes in, the 17th character will be lost because it has nowhere to go. The temporary storage is only enough for 16 characters. And the advantage is the processor need not go and read every single character as and when it comes. You still have some time before you really need to go and read characters uh, while still making sure that there is no data loss. Got it? So this allows host processor more time to read in the data and prevent loss of received data at high data rates. So if your data comes in very fast, the processor has still some time before it should really read the data, right? So it will go into the temporary storage location, which is what we call FIFO, first in, first out, which is kind of like a queue, just like how you queue in the canteen, right? If there are already 8 people in the queue, you will enter the queue as the 9th person. And when one person is served, the whole queue goes forward by 1. And similarly, when one character is read by the processor, the whole queue advances by 1. And which will be the first character that is read by the processor? The character which is at the head of the queue, at the beginning of the queue, front of the queue, which is the first character to have gone in. The first person to get served is the first person who entered the queue among all the people in the queue, right? If there are 8 people in the queue, the front guy is the guy who came in first. So same idea here. Okay, so the typical clock rate is at least 16 times the baud rate. Now what is baud rate? The rate at which you send data bits. Baud rate is nothing but 1 by bit period. Bit period is the duration for 1 bit, right? So 1 by bit period is your baud rate. So the two communication systems should have identical data rate settings. In fact, for two systems to be able to talk to each other, they should have identical settings with respect to the data rate, with respect to the number of characters you are using per data, or the number of bits in the data. Sorry, not number of characters per data, number of bits per character. It could be 5 to 8, right? Both the parties have to agree on it. Otherwise, the receiving party has no way to know how many bits to expect. So the settings should be identical on both sides. Again, parity, the number of parity bits used should be the same on both sides. If the transmitter is using a parity, the receiver should be expecting it. And same goes for the number of stop bits. Okay? The number of stop bits expected by both parties should be the same. The typical clock rate used is at least 16 times the baud rate, but it need not be always 16 times. There could be systems which use 64 or 32, etc. Which means if you are using 64, you will be sampling the incoming line 64 times a second to find the middle of the start bit. But 16 is good enough for most practical purposes. So one advantage of determining the middle of the start bit in each character or each frame is that your timing reference is fresh for every data byte that you receive, or for every character that we receive. By the way, the terms byte and character are mostly interchangeably used because, like I told you before, 99% of the time one character is 8 bits, which is 1 byte. Okay, so I might use the two terms interchangeably. So for each new frame, for each new byte, the middle of the start bit is computed afresh. So any error that occur in one byte will not affect the next byte, because your timing reference is fresh every time, right? But why do you have to do all these kind of stuff? Because you don't have a clock at the receiver. Receiver and transmitter do not have a synchronized clock. They have the same data rate, which doesn't mean the clock is the same, right? Because the clock use could be, transmitter could be using like this, the receiver could be using like this. It's the same clock rate, but it's not the same, right? The two clocks are not the same. So you need to recover edge information, or you need to make guesses regarding the clock used by the transmitter by looking at the received data. Okay, and that is the purpose of oversampling. Got it? So the transmission operation is simpler since it's under the control of the transmitting system. So only the receiver is this complicated. The transmitter is fairly simple, because when you are transmitting, you can use your own clock. You are entirely in control. Only the receiver has this complexity, because the receiver needs to make guesses regarding the clock used by the transmitter. So as soon as the data is deposited in the shift register after the completion of previous character, the UART hardware generates a start bit, generates the required number of data bits out on the data line, shifts it one by one, generates and append parity bit, and it also appends the stop bits. So since the transmission of a single character may take a long time relative to CPU times, the UART will maintain a flag showing a busy status to the host system, so that the host system does not deposit a new character until the previous one has been completed. Which essentially means, see, you are putting a new character into the shift register and it is shifted out one by one, right? So if the processor writes a new character while the previous one is still being shifted out, it's not very nice, because you might end up sending a part of one character and a part of another character, right? So what the processor does is, it will read a certain flag, busy flag. Some kind of a busy flag is maintained by the transmitter. So when the transmitter is busy, you should not write a new character. So the processor will first check whether the busy flag is set. If the busy flag is set, it will not write a new character. Okay, it will write only when the busy flag is no longer set, which means the hardware is no longer sending a data byte. This may also be done with an interrupt. So instead of polling the busy flag, you can use the busy to generate an interrupt if the system supports it. So once the previous character has been completed successfully, you will get an interrupt which allows you to write the next character. Got it? Since full duplex operation requires characters to be sent and received at the same time, practical UARTs use two different circuitry, including shift registers, etc., for transmitted characters and received characters. In other words, since it's full duplex, your transmit and receive circuitry operates more or less independently. Okay, you cannot really share hardware between the two. Unlike I2C, where most of the hardware used for transmission and reception is the same, because you either transmit or receive, not at the same time, right? Whereas for UART, it's not so much the case. Got it? Maybe you can take a few, maybe 3-4 minutes break to, catch your breath, or to go to the washroom before we continue. Hi everyone, welcome back. Uh, Give me a sec.